Oh, okay, dear colleagues, it's 11 o'clock in Moscow, and we are happy to start the second talk of today's morning session. Rinat Kashaev from Geneva will tell us about Teichmüller type TQFTs coming from local fields. So let's welcome.
Thank you very much. Thank you, the organizers, for the invitation. I'm very happy to talk in Russia, even if at distance. My subject today will be some class of TQFTs of what I call infinite type. So in the strict sense of the word, these are not TQFTs because the underlying vector spaces are infinite dimensional. And this means that the partition functions or invariants of three manifolds will not be always meaningful. For example, for surface cross circle, as we know, the TQFT partition functions are dimensions of the underlying vector spaces of the surfaces. So here it will be infinite quantity. But still, in the context, at least in the context of ideal triangulations and not complements, the partition functions in this context make sense, even if the underlying vector spaces are infinite dimensional. So here is my outline. So I will start by motivation through Chern-Simons theory. Then I will talk about classical dialogue as a motivation for the definition of a quantum dialogues, which will follow up. And then I will explain one class of examples coming from local fields. So to motivate my topic is I'd like to start from so-called Teichmüller TQFT construction known for at least 1 decade, which was accomplished by Johan Andersen and myself as a lift of the quantum Teichmüller theory into three-dimensional context. So as I said, so the underlying vector spaces are infinite dimensional. So the theory is functional analytic by its nature. And it is expected that this theory describes at least some part of the quantum Chern-Simons theory with gauge groups PSL2R and PSL2C. These are two groups which correspond to orientation preserving isometries of hyperbolic space in 2 and 3 dimensions, respectively. And in particular, the Chern-Simons theory at classical level, its phase space is given by the space of flat connections on three manifold given with values in the gauge group. And the question I would like to address today is if we can say something about the PSL2 groups, but considered over local fields. So R and C are included as examples of local fields. But the interest comes from the other examples, which are finite extensions of p-adic numbers, for example. And then my message will be that the formalism of the Teichmüller TQFT, with all this combinatorics behind of it, including the combinatorics of dihedral angles of ideal hyperbolic tetrahedra, will be relevant in the context of an example of a TQFT, of a solution of the system of equations, which I will be talking about later. And this example will come from any local field, so any local field is one of those examples, actually. So So even if you don't know what is a local field, as I did before recently, you can think just in terms of those examples. So this is just remind what is a classical dilogarithm function. Inside the unit disk, you can think of it as a series. These integrals allows to extend it into bigger domain. And here the most two properties of this function, which I will be generalizing to the quantum context. Of course, there are many more properties, but these two will be the most important for me. Here is a reason why dilogarithm function is important geometrically. So if we consider the ideal hyperbolic tetrahedron in three-dimensional hyperbolic space, then its volume is given by Milnor formula through this sum in terms of three dihedral angles, where the function is a Lobachevsky function given by the imaginary part of the dilogarithm function evaluated at the unit complex unit circle. So the dihedral angles will be important subsequently for me. Just keep in mind that combinatorially they are associated with edges of a tetrahedron, and on opposite edges we have one and the same value, like gamma here, beta here, alpha here. So three angles for three pairs of opposite edges, and they sum up to a constant given by pi. And now I'm going to generalize those two properties of the classical dilogarithm function into the quantum context. And the prototype of the general definition will be the properties of the quantum dilogarithm function of Fadeev, which underlies the Teichmüller TQFT. So now I'm going to just give the notions which will be used in this general definition. So I'd like to start from the notion of a Gaussian group. So let this T denote the complex unit circle. So a Gaussian group, by definition, is a locally compact abelian group, which means that it is an abelian group with integration, with Haar measure on it. And a Gaussian group is a locally compact abelian group with continuous non-degenerate t-valued quadratic form. This means that we have a function on the group with values in the complex unit circle, which is symmetric. And if we take this combination of this function, then it becomes a non-degenerate bicharacter. So usually about quadratic forms, we think in terms of additions. And so the difference is that in the target space, I write the abelian group multiplicatively. But if you switch to additive notation, then you will recognize just here the bilinear form associated with a quadratic form. So this is why I call it just a quadratic form. Okay, and then the condition of non-degenerateness implies that the group actually should be Pontryagin self-dual. So I will call this function Gaussian exponential, and the associated bilinear form Fourier kernel. So the Fourier kernel can be used to fix the normalization the harm measure, which I will do subsequently. And here are two examples. Three examples of Gaussian groups. For example, the real line with Gaussian exponential as a quadratic form. It has a direct counterpart for periodic numbers. You use just here the periodic fractional part, which is a rational number. So this exponential makes sense. And for me, will be important this third example, which is associated with any locally compact abelian group, B. Then by taking the product with its Pontryagin dual, we make it explicitly self-dual. And then the evaluation of a character on an element of the group can be interpreted as a quadratic form on the product group. And now here comes my main definition. So given a Gaussian group, A with a Gaussian exponential, then a quantum logarithm of such a Gaussian group is almost everywhere defined locally integrable function phi, complex valued function, which satisfies two properties. So the first property, the inversion relation, which says that the symmetrized product of the function is the Gaussian exponential up to a constant. For almost all x. So in my example will justify why I will say here almost all. So almost is with respect to the harm measure on the group. And the second property is the most important one, is a pentagon identity, which is following integral identity. So we have a product of two functions is equal to triple integral of the triple product of the function times some kernel. And the kernel is given entirely in terms of the Gaussian exponential on the group and the associated Fourier kernel. And there is some normalization constant given by this integral, which is always element of the complex unit circle. And the prototype example for this definition is Faddeev's quantum logarithm of the real line, so with the Gaussian exponential, which you have seen already, and then here is an explicit form of the function. So with respect to this definition, so it is a family of infinite family of examples indexed by parameter b. In particular, you can choose b to be equal 1, then it will be a more explicit function, which is essentially exponential of the classical logarithm function with the definition of which you have just seen in the beginning. And so it dates back to 19th century under the name of Holder's function, who was studying it through description in terms of infinite product. There are more examples, known examples, which come from quantum SL2 Sitchin-Simon theory, either through the Teichmüller TQFT or so-called 3D index invariant due to Dimov, Gayot, Gukov, Varanovich. No, Varanovich did just define the function before. He didn't do quantum topology, but defined the function back in 1992, I think. And here I will describe now my main example of today. So we take a local field. As I said, it can be real line complex numbers or finite extensions of periodic numbers or the field of formal power series in one indeterminate over a finite field. This is a finite field, so P Q supposed to be a power of a prime. So it will be useful to use a norm on the local field, which is not always the usual norm, which from which one starts describing the local field. But the norm defined through this formula is integer power of the usual norm on the local field. Okay, so but I will call this quantity the norm, even if it is not norm in the strict sense of the word. And here is a result that this. So remember that. Okay, so our local field is the following thing. We take our local field. So this should be this F, not this is our local field. I take a multiplicative group of non-zero elements of the local field, which I call B. And then I take its Pontryagin dual, whatever it is. And this will be my locally compact abelian group. And I take for Gaussian exponential just evaluation of the character, the first argument in the pair on the element of B, which is the second argument. So this is a Gaussian exponential. And the theorem tells that this combination is a quantum logarithm over that Gaussian group. And as you see that the function is not defined for any pair of alpha x, but only if x is not equal to -1, because if alpha is supposed to be evaluated only on non-zero elements of the field. But it's okay for a local field. Singletons are negligible, measured theoretically. So so it fits into the definition. So it is almost everywhere defined, even if not everywhere. And here is a general remark why quantum dialog over Gaussian groups is important, because given such an object, we have a canonical representation of the mapping class group of any punctured surface of finite type, namely any punctured surface which admits ideal triangulations, and this is a condition to have a ideal triangulation. So the set of punctures should be non-empty, and the Euler characteristic of the surface should be negative. And in the rest of my talk, I will describe how we can extend the formalism of the Teichmüller TQFT to this example. But the very fact that quantum dialog always gives a representations of mapping class groups hints to the fact that it has something to do with topology of three-dimensional manifolds. But I'm not saying that any solution will be lifted to a three-dimensional TQFT. So I know the examples where this is not the case, but it will be the case for this example. Okay, so as a preparation, I'd like to extend. I'd like to extend the definition to angle-dependent quantum dialogues, and for that, first I have to define what angle dependence means. So adapted to our context, so I will consider the angle space, which is just the space of pairs of a real number and a non-zero element of the field, and two components will be denoted by dot and double dot. So this pair carries an involution which consists in inverting the second argument and a distinguished element. So the first component will be written additively, and the second component is written multiplicatively. So these two elements live respectively as an element of the real number, while this -1 is a -1 of the field. And the positive part, C+, will be important subsequently, which consists of taking only non-negative real numbers as first components. And given a pair of elements in C+, we define psi AC of alpha x. So alpha x, as before, element of my locally compact abelian group. So this is a character on B, so element of B hat, this is element of B. And here is a definition, and as you see now the norm of elements of B enters into this definition. Still the definition makes sense almost everywhere, because this 1 minus a double dot x should be non-zero in order this norm to make sense and to be non-zero. And here the part which comes from alpha. So dependence on alpha is relatively simple in this expression. And the corresponding dual object, which is given by just a complex conjugation accompanied with a conjugated angle variables. So remember that I introduced this involution. And this long bar is just the complex conjugation, because this value lives in complex numbers. Okay, and here the two important properties, which I call tetrahedral symmetry relations. For the reason, the reason will be will come later. So I will associate these objects to tetrahedra, and then these two properties will correspond to symmetries of tetrahedra. And here now, besides of A and C, I use also B, which is related to A plus B plus C through the relation similar to dihedral angles of ideal tetrahedra. You remember we had high pi, but this time we use this distinguished element, which was fixed by this quantity. So it plays the role of pi. But if you divide the through geometric dihedral angles by pi, then the angles will sum up to 1. So think of this normalized dihedral angles as concerns the first component in the angle space. And then we have an angled pentagon relation, so 5-term integral identity, which uses indexed psi's, which are just psi's carrying a corresponding pair of dihedral angles. And we have 5 linear conditions, which literally correspond to conditions on the angles of dihedral tetrahedra, if you think of the identity in geometric terms. And then this is the preparation for the combinatorial setting of my TQFT. So it is a setting of order delta complexes. So a delta complex is essentially a CW complex with where all simplexes are all cells are simplexes, n-dimensional simplexes, and the distinguishing feature of simplexes is that they come together with dihedral of phase maps.
Excuse me, is there any connection with simplicial group structure so much important for homotopy groups of spheres? Simplicial groups.
I think that delta complex carries half of the properties of simplicial complexes. So for simplicial complexes, you have 2 families of boundary and coboundary. So you have the degenerations also in simplicial complexes, but here you don't have degenerations. We use only boundary maps. So it's a half of properties. I don't know, maybe the degeneracies, of course, you have the degeneracies in this context, but I'm not using them at least. Okay, so what is the specifics about the delta complexes is that, so if you take boundary inclusions, so these are just inclusions of simplices of 1 dimension less as a part of the boundary of n-dimensional simplex, just given by this kind of inclusion. You put 0, 1 of the n coordinates, and just spread out the other coordinates in as the rest of the components. And the condition is that if you compose a characteristic function of a cell with phase inclusion, then you will get a characteristic function of low dimensional cell, which we call the boundary of the cell di alpha. And as usual, so the boundary maps satisfy these properties. And here is the example of a delta complex, which is the simplest example in 3 dimensions I know of. So it is given by one single. So X sub I denotes just for the set of I-dimensional cells. So you see we have 3-dimensional cells, 2-dimensional, 1-dimensional, and 0-dimensional cells. So in this example, we have one single 3-dimensional cell, which corresponds to this tetrahedron. And we have only one 0-dimensional cell, which means that all vertices, these 3 vertices, are identified. And we have 2 cells in each other dimension. So 2 1-dimensional cells, or 2 edges, and 2 2-dimensional cells, or 2 triangles in overall. And in this tetrahedron, so we have 4 triangles as part of its faces, and they identified pairwise. For example, this triangular face is identified with this triangular face by respecting the orientation on the edges. So so that gamma identification is just like bending tetrahedron along this edge, the way that it closes up like a book. And the other pair of faces, beta, identified in more intricate way. It is less evident, but the only rule is that you have to respect all the arrows. For example, this vertex, which is a vertex through which one arrow comes in, another one comes out. So it should go to the similar vertex of the second beta phase. So it is this vertex. So this beta phase, think of the outer region of the tetrahedron. So think of the boundary of the tetrahedron as a two-sphere, which is identified with a plane with 1 point and infinity. So this beta phase is not a backside phase as we usually think in three-dimensional perspective, but just the outer region of the plane. So it is completely visible. And then, so you see these two edges of this triangle, and this vertex goes to this vertex in identification. And so on. Okay, so this is the example of a delta complex, which, by the way, triangulates, corresponds to S3. S3. As you see, it is very economical. So if you want a triangulation in the general sense of S3 into one single tetrahedron. Okay, and then so the delta complex, which represents a given oriented pseudo three manifold. So pseudo means that I admit the vertices to be singular points in the complex. So typically, the ideal triangulations are examples of such pseudo three manifold because, for example, in the ideal triangulation of a knot complement, so the vertex of the ideal triangulation is where the knot is. So, so its neighborhood is not a three ball. It is a cone over torus. So should I read the questions? And because
Well, it's up to you. So you can do whatever you want. Maybe after the talk.
yeah, okay. But it's better to stop me orally and ask questions instead of writing. Okay, so in an oriented setting, we have two types of tetrahedra, positive and negative. So just think the following way. So put the minimal, so remember that the vertices are ordered. So we have zeros vertex where all arrows come out, and then the first vertex where one arrow comes in and two arrows come out, second vertex where two arrows come in and one arrow come out, and the last third vertex where all arrows come in. And if you put the minimal vertex in the center and the first, I mean the next vertex on the top, then you have two possibilities for second and the third vertices. Either second finds itself on the right or on the left. So depending on that, I call the tetrahedron positive and the negative. And correspondingly, we have a sign function on the set of three cells of the delta complex, which is equal to 1 if the tetrahedron is positive and -1 if it is negative. And now we decorate our cells with angle data. So we take C+ shapes. I mean, recall that my angle variables are two-component variables. So first component is real, which we can think in terms of true dihedral angles and normalized in the units of pi. But the second one is multiplicative, comes from my local field. And I impose the properties of the dihedral angles, namely, for each vertex, the three angles sum up to a constant. Remember that this was a two-component guy given by 1 minus 1. And so the opposite angles are equal. And one more technical detail. So we have some gauge group action, which corresponds to just think in terms of Poisson brackets. So I take Neumann-Zagier Poisson bracket, even if these are two-component objects, just think as if they would be one-component object. And then any Poisson bracket induces some group action by applying. So you take a generator as some function in the Poisson manifold, and then Poisson bracket of this function with any other variable gives some infinitesimal transformation, and this is the group action which I'm talking about. And in the case under consideration, this will be some linear group action in the space of angles, which I call gauge group action. Why I need this gauge group action? Because in the end my partition functions will be gauge group invariant. So it means simply that the partition function will not depend on all the dihedral angles, but only on specific combination of them. And then we have a Pachner angle Pachner moves, where you should take into account the presence of dihedral angles. For example, on this edge, the dihedral angle should be given as a sum of dihedral angles coming from two tetrahedra which share this edge. And then, so I'm starting heading myself towards the partition functions with the notation for the space of maps. I consider the distribution valued quantity associated with a tetrahedron. At this stage, it is a model independent. So you see the definition uses only the Gaussian group structure. So you see here the Fourier kernel. This is a sign of the tetrahedron, and delta functions on the locally compact abelian group. So no any other specifics of the model, and no angles at this stage. And so under the mild topological restriction, so the following kinematical kernel is well defined. So you take a product over all tetrahedra, which means that you multiply all these distributions all together and integrate over phase variables. So these four variables sit are on two-dimensional cells. You see this. This is reflected in this part of the definition. And another variable sits associated to the tetrahedron itself. It is a y variable. Okay, so you integrate over all phase variables here, and then the result becomes a distribution valued object given on functions on three cells. And under this condition, this is well-defined distribution. And this second part is what I call dynamical content. It really depends now on the logarithm function. So remember, these are the angle-dependent quantities, and I associate to each three-dimensional cell a weight function given by distribution-valued weight function, which takes two possible values depending on the sign for positive tetrahedra and negative tetrahedra. And the dynamical content is just a product of those guys over all tetrahedra. And the partition function is just a contraction. So you take a kinematical kernel, multiply it with the dynamical content, and integrate over all variables sitting in tetrahedra. And you end up with something which depends now only on angle data. This is just the angle variables. And the theorem is the following. So if we have an admissible admissible means that this topological condition under which the kinematical kernel exists, this is admissibility. So if we have an admissible closed triangulation with a shape structure given by this variable, and we call the total dihedral angles around geometrical edges by tau, then this partition function is well-defined, and it has three properties. So it is invariant under shape gauge transformations, provided that the norm of each total angle around the geometric edge is 1. For example, if you want to balance, so you should put them to be equal twice this constant pi. And this property is satisfied for such special cases. Second property, all 2 3-Pachner moves are satisfied along balance edges. So balancing means that total angle around geometrical edge is 2 pi. And all edge you can change all edge orientation as well. So this is a story of tetrahedral symmetries. If you remember some number of slides ago, I mentioned the symmetry relations when I defined angle-dependent quantum dialogues. And here is the example of explicit calculation. So this is the same delta complex I talked about the triangulation, one tetrahedron triangulation of the S3. But of course, since it is not ideal triangulation, we cannot balance all the edges simply because we cannot maintain the consistency conditions with interpretation of dihedral angles. We have overall 2 geometric edges, blue edge and the black edge. And if we impose total angle to be gamma on blue edge, then on the other edge, necessarily the angle will be the 2 pi angle minus these angles on the blue edge. And so this topologically, this corresponds to a cone structure on the wedge of 2 circles embedded into S3. So if you want, we are talking about some hyperbolic 3-manifold given by a cone structure along a wedge of 2 circles embedded into S3. And the cone structure given by this parameter gamma, which is in my case 2-component thing. So it will depend on 2 components, gamma dot and gamma double dot. But this example I use just for illustration of the general theorem. So if you calculate this partition function without imposing any conditions, so the answer will look like this, some combination of norms of angles. And as you see, and here is a gauge transformation. So gamma is gauge invariant, but alpha and beta are not gauge invariant. So if you shift alpha by quantity lambda, then beta is shifted in the opposite direction by quantity lambda. So to have a gauge invariant quantity, we need it to be independent of alpha and beta. But as you see here, the answer depends on beta gamma, but on beta, sorry, gamma is gauge invariant quantity. But if double dot part of gamma is of norm 1, then dependence on beta dot disappears. And this corresponds, exactly corresponds to what I stated in the theorem. So if the total dihedral angle around the geometric edge is of norm 1 as concerns the double dot part, then the quantity is gauge invariant. And then this is illustrated by this quantity. You see that gamma is total angle around blue edge. So if its double dot part is of norm 1, then the partition function is gauge invariant. It depends only on gamma part of the angles. Okay, now I'd like to briefly talk about two other TQFT models. This time they are of Turai-Viro type, and algebraically they correspond to two exact sequences of locally compatible groups which interfere in our context. So remember that this A was B hat cross B. And then we have natural two exact sequences. B hat is included into R as the first components with the identity element in the first one. Then the corresponding quotient group is naturally identified with B. And what is important that these two guys should be Pontryagin dual to each other. And likewise, we can embed first B component, and then the quotient will be isomorphic to B hat. And each such sequence gives rise to a Turai-Viro type in general context of the Teichmüller TQFT formalism. So, and the local states associated to edges will be elements of this group for this sequence and of this group for this sequence. Correspondingly, the model coming out from this sequence I will call B model, and for that one the B hat model. And here is a tetrahedral rules. So we have a Turai-Viro type model. So the local variables live on the edges now, which are indexed by xij, if we enumerate the vertices. And then the tetrahedral weight is given by a certain function of two angle type variables, where the dependence on the state variables enter through two combinations of angles. And it is the distribution value. So there is a delta function part and some norm dependent part. So you see that the xz correspond to local state variables and the AC correspond to angle variables here. And all of them mix up somehow. And here is the example of calculation which motivates myself very much. So we recover the A polynomial of a knot. So this is a calculation for figure 8 knot complement. So we recover the A polynomial of the figure 8 knot as an argument of delta function. But the whole partition function is not just the delta function, but some normalization part, which so it is not just the reproducing the A polynomial, but A polynomial with some specific normalization, which is also part of the invariant. And second example is a B hat model, which is kind of dual model. This time, local variables live in the dual group, in the B hat group. So the structure of the tetrahedral way is very similar, still a certain function, this time on pair of. So here I'm using the multiplicative notation, but in reality it should be I use additive notation, so never mind, it is shorter to write it this way, so as a result it fits into the screen. And the function g, which enters the B model, is related to function h, which enters in the B hat model through Fourier transformation. So you see a pair of variables on the B group, it's transformed to a pair of variables on the B hat group. But this time, the partition function is very different in its nature. It is a some period integral. So it shows up as a very concrete integral along the real line. So the absolute value of real numbers, and then some exponents given by real parts of the angle variables. But integration is accomplished along on the curve. And as a matter of fact, this curve is nothing else but the apolynomial curve of the figure 8 knot, which you can see, say by calculating its discriminant, for example. Okay, so I stop here, and thank you for your attention.
Okay, thank you very much for a wonderful talk. Okay, are there any questions or remarks or comments? I have written a couple of questions in the chat, so maybe you can comment on them a little.
In the chat?
Yes, yes.
Maybe you can repeat your question, because it's easier to listen than.
Yeah, sure. So the first thing is that the axioms of quantum dilogarithm or whatever Gaussian group seem to be very similar to the definition of the group gamma. So hence they should give invariance of many things, not only of three manifolds that you can be very familiar with, but also with braids, and also vice versa. So the things we used for gamma and for our axioms are related to yours because of the pentagon. So because the pentagon is the crux of the matter, because roughly speaking, pentagon appears everywhere, and so of course you have invariance of three manifolds. You have Pachner 3-2, but this is also, for example, Biedenhardt-Elliott. And this is, for example, the same as Matveev-Pergolini, and I can also give another list. So I think axioms in many theories fit to each other, and relations from one part can
but
fit into...
algebraically, often it is not clear how one kind of solution you can relate to another solution. So, for example, typical way of getting a solution of pentagon is from Hopf algebras, right? The pentagon can be looked at as a encoding all the Hopf algebra axioms, for example. At least in the case of finite dimensional Hopf algebras, you can just establish one-to-one correspondence between finite dimensional Hopf algebras and finite dimensional solutions of the pentagon. But to the best of my knowledge, it is not known how to translate the Hopf algebra axioms into the properties of 6J symbols, because 6J symbols also solve pentagon. But it is not known if any 6J symbol corresponds to some kind of Hopf algebra in some category. This I don't know.
Okay, thank you very much. I will think about that. One more thing is that at some point you mentioned angle dependent or angle independent. So in my opinion, we shouldn't restrict ourselves into the category when we have just edges or just edges with a bit of angles. So actually, I was suggesting to use some notion of data, which can contain everything. Well, edges, areas, volumes, angles, whatever else. And if it satisfies some naturality conditions, which can again be related to angles, edges, and so on, then it gives a solution to a pentagon in whatever form. And by whatever form, I mean we can have a matrix form or tensor form or maybe integral form.
Yeah, but it is similar to, you say, if you take Young-Baxter equation, there are different forms of Young-Baxter, right?
Yeah, sure.
But it is not always clear if, for example, even set theoretical Young-Baxter is after all Young-Baxter, but how set theoretical Young-Baxter equation is related to quantum Young-Baxter, it is not always clear, right? You can sometimes you can relate finite, solutions of set theoretical in finite sets by producing vector spaces generated by elements of the finite set, but it is not always clear. So it is not, I don't agree that saying that whatever form it answers all questions. Not at all. So each form can be interesting by itself.
Okay, thank you very much. Any further questions or comments or remarks? Yes, please.
Yeah, no, thank you very much for your talk. So I have a couple of questions. The first question about your new versions of the algorithm function. Is it possible to give possibility to formulate new kind of volume conjectures?
But it depends on for Teichmüller TQFT. Yes, we have you see that the solution is a one parameter family, and then the question arises: if you define the quantum invariant for each element of the family, then you have a family of invariants, and then you can ask the behavior of this family when you send this parameter to some limit, and there is indeed a volume conjecture property. Behavior where, but the difference with the Colour-Jones polynomial is that when this B variable, let me go to this example just to have a solution in. Yeah, so I'm talking about this example.
Yes.
So that when B this goes to 0. Then the partition function goes to exponentially decays, goes to 0, and the decay rate is given by negative volume. Indeed, in this case, there is a volume behavior. But for example, if you fix B by fixed value, like B equal 1, then the partition the invariant will be just a number, not a function. So it doesn't make sense anymore of some volume-like behavior. But on the other hand, this invariant is kind of classical invariant, which is given as a sum of solutions of hyperbolicity equations in the complement of the knot, for example. And and then the question arises: what kind of what kind of function it is on the space of hyperbolic structures, or on the knot complement. But yeah, okay. So different kind of questions you can pose, and likewise in the example I talked about today, there is no parameter. Like quantum parameter like B here. So there is no probably meaning of talking about volume conjectures, but still we have a contact with a polynomial which describes the presentations and PSL2C, and then we can see what properties of the space of flat connections probes this invariance.
And okay, thank you. And also another short question. So you considered different local fields. So it means that you go to some kind of arithmetic groups.
Yeah. So again, so concerning this parameter, you can introduce this parameter through considering a family of finite extensions of QP.
Okay.
Through irreducible polynomials, and then the degree of extension can play the role of Planck constant, for example.
So you fix a field for the other angles, so you consider everything in this given field. So it's
yes. So, but I can consider family of field extensions. Family of fields, okay. And then try to see different behaviors.
Okay. Thank you.
Okay, thank you very much. Maybe some very short question. So if there are no more questions, so let's thank the speaker again. We'll resume very soon.
Thank you.